Thanks. So just to level set, this talk is about a package that I created at work for basically to make my own work easier, and went through the process of open sourcing it because I think it was general purpose enough that it could help a lot of people. But the talk is going to be split into two parts. The first half is more like conceptual thoughts about like software complexity, what makes good software, bad software. If you were at Chris's talk yesterday about guardrails, there will be some similar ideas floating around. And then the second half will be about Labrea. It'll be a lot of code on screen. So if you might want to move closer if you find it hard to see. I tried to make it as big as possible, but yeah, so we'll get into it. Yeah. Okay, so who am I? I'm Austin Warner. I'm a data scientist at 8451, which is a subsidiary of Kroger. We're basically like the data analytics powerhouse, sort of like, it started as a consulting firm that got brought in-house. It's a confusing relationship, but think of it as Kroger. And I'm the tech lead for a large coupon recommender system for loyalty marketing. And I'm a data scientist technically, but really my job is like day-to-day is software engineer. I've been using Python for 10 years now. I'm a big advocate for functional programming. I come from a pure math background, so a lot of the guarantees you get from functional programming really appeal to me. And I live in Cincinnati with my wife Hannah and our dog Rory. Okay, so the software complexity crisis, as it's been coined. So as we know, we keep asking software to do more and more. We're creating bigger systems, more complex systems. And there's some common approaches to building software that just fail to adequately address that complexity, and just they can't stand up to as the system grows and there's more interconnection and there's more just issues that arise with the complexity that comes with large systems. And so this quote, the biggest problem in the development and maintenance of large-scale software systems is complexity. Large systems are hard to understand. So this is from a paper called Out of the Tar Pit, which is, you know, the homage of the subtitle of this talk, Leading You Out of the Tar Pit. This is a really great paper. I recommend that anybody read it. It's an academic-ish paper, but it's not really academic. It's more conversational. It's just talking about what are problems with software. And this is almost 20 years old now, and I think it still stands true, a lot of their observations. Some things have seen more widespread adoption, but there's still like a lot that can be learned from this paper. So one thing I really want to focus on in the first half of this talk is the difference between two concepts. And the first of those is, what does it mean for something to be easy? So when we're writing code, we really like to focus on what does it mean to make code easy to write. And so ease is about familiarity or skill. So we use this word a lot. We say like, oh, it's easy to do this. We love to say that Python is easy. Important things is that it's a subjective thing. It really doesn't say much about the code itself. It's more about what is my experience of writing the code. It's quick to do. It doesn't take a lot of mental effort. But there's a lot of things that you can do that are easy that lead to bad outcomes. So like if I'm putting away my clothes, I can just dump it in a pile. That's easy. That doesn't mean that it's the right way to do things. And so like this urge to make things easy, I think, is a trap that we fall into sometimes. But it's important. Like, if you don't ever make things easy, then you really slow down. You can't write code quickly enough to be productive. This is in contrast to a related concept that I think we use these words interchangeably, but they're very different. This is the idea of simplicity. Also, I meant to say, this entire first part, if you've seen Rich Hickey's talk, Simple Made Easy, he's the creator of the closure language. That's an incredible talk. He talks about this entire concept for an hour. You should watch that talk. He puts it in much better words than I could. I'm trying to distill it down into like 4 slides. But the difference between easy and simple is that simple is about separability. If you go back to like the roots of these words, like the Latin of it, simple is rooted in this word simplex, which means one twist. So it's the idea of like things are not tangled together, where complex is many twists. So you've got things that are tangled together, and we all know the idea of spaghetti code. That's complex code because things are twisted together. There's these relationships between things, and things are coupled, and you can't
look at one piece of the code and hold it in your head without thinking of all the different ways that it interacts with the rest of the system. So this is something that we should really aspire to, is how do we make software simple so we can look at one piece of it, change it, and not have to think about all the interactions with the rest of the system. But the fact that colloquially we say easy and simple interchangeably leads to some serious problems because we think we're doing something simple, but we're actually just doing something that feels easy to us. So Python is easy, and you'll hear that a lot, that like this, you can't really read it, but the bottom left is showing the Stack Overflow survey from 2024 of new developers, and it's the #1 programming language for new developers. People love to learn Python because it's easy, you know, the lightweight syntax, all of that stuff. And like I said, that is good, that is important to make it so that you can write code quickly and you don't have to deal with the boilerplate and all that stuff. But Python code bases can become very complex, and so we've seen, in reference to the guardrails talk, if you were there yesterday, there's been a lot of guardrails that we've added to the language, like type hinting and context managers and the async and all of that stuff that can simplify some complex concepts to make it easier to write high quality code. But there's still some fundamental things I think about most programming languages that lead to complex code, but in particular in Python, shared references to mutable objects. That's a really big problem because if you have two different parts of your code base, you know, it's the classic, like you leave the default argument is a list in a function definition, and then you get your weird foot guns where you mutate a list and you're not expecting it. But there's like mutable objects, like stateful programming that can lead to complexity that leaks into the rest of your program. And there's issues with reusability and composability and some of the base Python stuff. It's very easy to write tightly coupled function definitions and classes with inheritance and stuff. So there's a lot of stuff that you have to avoid doing that Python lets you do because it's this powerful multi-paradigm language. But if you want to write simple software, sometimes you have to avoid the more powerful features unless you really need it. Functional programming is one of these approaches that you can take that gives you a more simple code base because functions are simple. So functional programming is simple because it's built on these very simple primitives. You use immutable data. You don't mutate data in place. You write pure functions. Functions take an input. They always return the same output. And that's the fact that you have these fundamental components that do exactly one thing and you can compose them in ways like this leads to a simpler code base. The problem is it's just really hard to do. And in practice, especially in a multi-paradigm language, because you have at your disposal these seemingly really powerful tools like classes and inheritance and mutable data, and it's so tempting to just use those things at like anytime things get hard, you think, oh, I could just update that list in place and that would be so easy. But you have to fight that temptation and do the simple thing. But there are languages that have addressed that, like I'm a big advocate of looking at different languages for inspiration. Pure functional languages have solved a lot of stuff around like how to handle the mutable data problem, but one thing that I have not seen a good solution for in any language is this unwanted coupling between function definitions, which I will get into in the second part of this talk. But there's a few different ways that this kind of manifests. One of them is as you're passing arguments through nested function calls, the outer function has to know about all of the arguments of the inner function. That becomes messy. Sometimes you have these functions where it's like implicit that you're going to call one function and then feed the output of that into another function, and nowhere in the structure of the code is it clear that that's the intended path. And yeah, like pure functional languages just I don't think have solved for this. And Labrea is an attempt to solve for that problem in Python. So I'm going to walk through in a few slides some examples of how I think it addresses that problem. It's a bit of a paradigm shift from standard Python programming, but I think it's useful. I don't think it's something that I would say every Python project should use, but I think you should consider it. So I'm going to take a quick detour and kind of talk about where I'm coming from with my work and why I was led to create this package. So this is the sales pitch part for Kroger. So Kroger, if you're not aware, largest grocer in the country, we have this best customer communications program, which is loyalty marketing, where we're sending out coupons for things that you already buy for the most part, just to say like thank you for shopping at Kroger. The biggest part of this broader program is something called the Loyal Customer Mailer, and it's about more than 10 million households each month get a unique set of 12 coupons for things that they already buy, and it's coming from this pool of over 1,500 possible coupons. And there's all these business constraints we have to follow. So like a big one is we care a lot about data privacy and things of that nature. And so like there's a lot of, I can't think of the word, but there's a lot of things we have, considerations that we have to make around data privacy. And then we have like legal restrictions, and so like this offer, we might only be able to send out 100,000 of it, and this offer we can send out 500,000 of it. So we have all these different interacting constraints, and this gets very complicated to come up with. You feed in all these possible households and offer or coupons, and get out on the other side like an output of you get these 12, I get these 12. And so we had a code base that we were using to implement this, and we used the standard approaches. So we had, we broke things into functions, put things in modules, we were doing unit testing and type checking and linting, and we were avoiding mutation at all costs. We were always trying to create new data as opposed to mutate. We were doing things as declaratively as possible, where we would use configuration files to drive the actual execution. But this system grew to the point of 20,000 lines of code, which is a pretty large code base, and it was a pretty small team. But it just became harder and harder to make changes because with all of these connections, you changed something in one place, and it felt nearly impossible to confidently say, if I change this one thing, it won't break anything over here, unless you tested the entire flow end to end. And sometimes even you had to test the flow at full scale, which is a very expensive thing when you're talking about the scale of data that we're working with. And like I said, if you were at the talk yesterday about guardrails, that's a very defensive approach. You just kind of test it and hope that your tests will catch any problems, and that's a scary place to be when you have the amount of money riding on it that we do. So we have the primary problem we found was this unwanted coupling between functions. Foo was always receiving the output of bar as an argument, and like I said earlier, like nowhere in the code is that actually formally declared. You just kind of have to know from experience. Like foo calls bar, needs to pass the arguments through, so like there's things like you can use quargs, but like eventually if you're calling multiple functions and they're expecting the same argument name, it just becomes a whole mess, and it's really hard to adequately do all of the wiring in this massive code base to make sure that the data flows through correctly. We couldn't make changes confidently without running into issues. So we had what, like, on the surface was a composable system, but it had just become spaghetti code, and we didn't understand why, because we had followed all of the best practices. And so what we decided is that we needed to do like a full rewrite focused on true composability, which meant we had a rules-driven architecture, so we would just say, like, here are my inputs, and I can declare these are the rules I'm enforcing, and then the output is whatever I fed in that met those rules. Config-driven, like I said, and like each rule was this encapsulated filter. I could talk about this. This gets more into like the pure math of it, but this was sort of like where we went. But the big thing is that these individual plug-and-play rules that we wanted to use declaratively, they had data that they were dependent on. If I wanted to enforce a rule, I might need to run a database query to identify which customers were affected by that business rule. And I didn't want to have to know, like, I wanted to be able to just say, enforce this business rule, and that thing could know oh, I need to run this database query, pull the data in and enforce as necessary, rather than me have to, every time I change something in one of these campaigns, because it's constantly changing, the business environment is constantly changing, didn't want to have to go in and update all of the inputs all the time. So this is what motivated the creation of Labrea. And I'll get into what Labrea actually is in a minute, but just first a disclaimer. We're talking about software complexity, and it's just impossible to adequately convey a large, complex system in a 30-minute talk on a PowerPoint slide. Like, we're talking about the code base I was working in was 20,000 lines of code. The problems that we're talking about seem insignificant in a single script. It's as the project grows and expands that these connections just overwhelm the system, and suddenly you're at a point where you realize, oh, I can't change anything anymore. And so I just want you to, as you're looking at these code examples, just remember that in this small example, you do not need to take this approach to solve for complexity. You can just handle it. You can read the whole script and understand it in your head. But think about it as if you were building something where you were working on a large code base. How would you handle that? And also just remember, like, once you get to the point where you have a large code base, you can't go back and fix it. You have to start. You have to do things in a simple way from the beginning, because like we did, we got to that 20,000 lines of code and we had to rewrite the whole thing. There was no incremental fix to go, like, we had a disease that had permeated and we had to eradicate it and start over. So just think about that as you're looking at this code. Okay, I'm running a little behind, so I'm gonna speed up. Okay, so what actually is Labrea? Labrea is this backbone that unlocks composability for us in my specific work, but it's very general purpose. It's a way of writing your programs based on these two concepts. So we have these two fundamental concepts are options and data sets, and options are just any user inputs, and we say that our options are all JSON. So we have a JSON configuration file, and we provide all of the user inputs to our program. And then we have data sets, which are blueprints for how could I take those options and perform some computation on them and create some data. And then you can combine those data sets and say, oh, I did some computation, created some data, and now let me combine 2 of those or 5 of those and build up this tree. I see we also had the talk yesterday about graphs. This is another instance of modeling your entire program as a graph, and it's a very powerful one. And we're not going to literally build a graph in the program, but the Labrea is sort of building that graph for you, and it leads to some simpler programs. So I hope that this text will be readable. We're going to start looking at code. So this is just a side-by-side comparison of a very simple program that you've got some data, you've got some stored data and some transactions data, and you might just want to see how much did I sell by like store region in the set of transactions that I'm looking at. So on the left, it's pretty simple. You've got some configuration on the top, some paths to the stores and the transactions data. You have functions for reading in that data, a function for combining those 2 pieces of data, doing the aggregation and returning it out. And then the main method at the bottom does the actual execution of like reading in the data, passing to the aggregation function, so on and so forth. We're not doing anything with that output in this example, but just imagine, again, this is one piece of a larger system. And then Labrea on the right, as you can see, pretty similar. The difference is you'll see these data set decorators, which we'll get into what that actually means. I'm going to step through this example on the right piece by piece, and we can kind of get a feel for what is different and what's the same. So first piece, like I said, we're still keeping our configuration in a dictionary. We did that on the last example as well. But yeah, this basically, one restriction is that this has to be valid JSON. And we created it in Python here, but like in practice, you would think of this as being stored in like an external configuration file or something of that nature. Then the first piece, I'm gonna kind of start zoomed in and then zoom out. This very small place where there's an option object. So you have an instance of this option class, and an option object represents, I would like to retrieve some configuration from my options. So I'm saying, oh, I need to know the path to the store's data for the current computation that I'm doing. So you just say option paths.stores. So that's like a nested dotted key. And that option object, if you were to give it that dictionary of all of your configuration, it would just spit back out the path. So we say that you evaluate the option with the options dictionary. So that's like the most fundamental starting point. Like you think all of the leaf nodes in your graph are options. That's where you pull in all of your inputs. But then as you zoom out, this stores data set, it looks similar to a normal function, but you take it and you decorate it with this data set decorator. And basically what that says is, I want to have a data set object, which, like the option, I can evaluate it with the options dictionary, and it will pull the necessary options out. It will recursively look at all the dependencies. So that paths.stores option is a dependency. It says, oh, I need to pull the paths.stores option in, pass it in as the path argument, and then run the function body. So if I were to call that stores data set like a function, it just takes one argument, and it's the options dictionary, and it would do everything for you. It would automatically pull the inputs, route it as necessary, and then return the value. So that's one data set. That's small. The transactions data set, the same thing. It has an option that when evaluated, it'll pull the transactions path, feed it in, read the data in, and then return. But the big thing is that when you get down to this aggregated data set, again, it's going to recursively go through and do all of this evaluation. So when you call that sales by region data set with an options dictionary, it will evaluate the stores data set, which it has a dependency on, which recursively goes through, evaluates the options, does all of that, and then pass it in as an argument. And then it does the same thing for a transactions data set. It recursively goes through, evaluates all the dependencies, and then passes the value in as an argument. And so what we've done is we've turned all of what were functions that we were calling in series, and we've turned them into functions that have the same signature. They all take exactly one thing. They take this options dictionary. So now when I say, oh, I need to pass transactions data into this function, I don't need to go and manually pull it and remember which arguments do I need to pass. I have predefined this function will always pull this input in for my configuration anytime that I use it. And so then you can reuse those data sets anywhere in your code where you're creating other data sets. So it kind of allows for this reusability, mix and match, compose data sets together and build more complex calculations. And then you'll see down at the bottom, you've just got like the main method. All it does is pass the options dictionary in, and everything else happens. I want to be clear. The point of this is not to replace general purpose functions like the sum function that's a built-in. Like those functions you use a million places in your code. But when you have large application code, a lot of times you have these functions that you write a function and call it in exactly one place, and then you feed the output into another function. And you have functions that are used more as like units of, like just as organizational units to say, oh, this is the recipe for creating this data, this is the recipe for creating that data, and that's good, but it leads to this problem where you don't know where all of the wiring becomes very opaque, and it's hard to know how the functions relate with each other. So, what's the point of all this? What if we wanted to change this program? Like, we had this program, sure, it looked basically the same to do it the old way versus the new way. And imagine if you wanted to change this, where we're gonna say, oh, instead of reading all of the transaction history in, we just want to filter it down to a specific window. Without Labrea, you would have to update your function to take that as an argument. You would need to update your configuration to include the start and end dates. But then also, in the actual calling of that function, you need to find where that data needs to get fed in, where those inputs are required, and pass it through. So like, imagine, this function is only being called once, but if it's being called in like 5 different places, you need to find all the places where that function is being called and adequately route your inputs through to make sure that it's being used properly. But with Labrea, you don't have to do any of that. You just add the options to the data set, and anywhere where that data set is being called, it'll automatically pull the options in as necessary anytime that data set is evaluated. So the big thing is you don't have to change any of your downstream callers of a data set. You just say, oh, this data set needs new inputs, and I add those inputs to my options, and everything between those 2 points, it's completely abstracted away. There's no need to know that, oh, I'm calling a data set that needs this input. It just all gets routed and wired together automatically. So yeah, we've sort of successfully, in my view, removed some unnecessary coupling between functions. And again, remember, we're looking at a small example, but if this was a massive code base where you've got lots of nesting of functions, you have to route all of those inputs through. And the current approach is there's different ways you can handle it, but they tend to have pretty big negative trade-offs you have to consider. But yeah, now we don't ever have to, if you change the implementation of a data set, you don't have to do any downstream changes. Any users of that data set don't need to know or care how it's implemented. They just use it. And the only thing you need to change is the one spot where you create your options, and everything else just works automatically. So yeah, seems like a small thing in a small code base. It is a very small thing, but when you're writing large code bases, that wiring and routing of inputs is can become the majority of the program. And so not having to deal with that can really free you up to think about the essence of what the program is supposed to do. So I'm short on time. I'm gonna real quick blow through the next 4 slides. There's other advantages to this. Debugging, if you wanted to debug part of your program currently, with normal approaches, you need an IDE with a step-in debugger, and you have to work all the way through to find the area where that piece of data is created. Now you just call that data set with the options, and you know what that's going to return. And anywhere where that data set is used, sorry, I should have skipped to the next slide. Anywhere where that transaction program, it'll have the same value. So you don't have to worry about using some fancy IDE. You could do this in production. You could go to your production servers, do a interactive Python session and just evaluate the data set and just see what the value of that would be. Polymorphism, I'm seriously oversimplifying here, but one of the big values of this is, I'll just actually skip this slide and go to what Labrea actually does. There's this idea of overloads, so you can have one data set that has multiple implementations, and so you can say, depending on the value of an option, I want to use this implementation of a data set or this other implementation of a data set. And you can have this kind of complex dispatching, and that makes it very easy to think about, again, what is the essence of the program? I have some idea of what my transaction data is. I don't really care how it gets read in. I might want to use a flat file. I might want to use a database. Doesn't matter. So, takeaways. Easy and simple, not the same thing. We should be more precise in our language. We should really try to use those as different words. You should focus on simplicity when you're writing software. It makes things a little bit harder at the beginning, but it makes things way easier at the end. And then I think Labrea makes it easier to write simple software, and I think you should consider trying it next time you are starting a project. Thank you.